My name is Bertrand Marquis. I'm software architect at ARM, and this is Stefano Stabellini from AMD Xilinx. Sorry.
Yeah, hi, I'm a fellow at AMD.
And today we will present you the Xen safety certification work and the progress so far and plan for the future. So first, why do we do that? So over the last years, the automotive industry started to evolve very rapidly to include more and more software in their car. We also, in our cars, new features, software-based, like for driving assistance. Our cars are more and more helping us. There are systems where they are even almost completely driving for us. For entertainment, we have more and more connected systems with evolved GPS. We can use apps to control our cars, stop our car, close our cars, so our cars are connected. And now some of them are even doing automatic software update over the year. And in general, all car manufacturers are now starting to work on autonomous driving. This was something that we all thought was impossible 5 or 10 years ago. It's now a reality. There is no car manufacturer in the world at the moment which is not working on this subject. So this is coming. When this is coming is a big open question, and how this is coming is also an open question. So all those new functions are adding a lot more critical software workload on the car. The software is becoming more and more complex. It's involving video processing, artificial intelligence, and a huge number of sensors. And all this requires more and more computing. On average car now includes hundreds of MCUs, which are not anymore small microcontrollers. The fact that cars are more and more dependent on software is bringing some new challenges. And those challenges will be tough for software. Mainly, we will have to go to safety, and safety certification will become a real subject for the automotive industry. But this is not only the automotive industry. We see this trend in other markets. In IoT, where we have more and more connected devices, and some of them become critical for life. And also in robotics, because there are more and more autonomous robots out there, and some of them can harm your life. And all those markets will also go to some safety constraints in the future. So there are a number of products out there, and not only cars, which will have safety requirements in the future. So we are leading toward a software-defined vehicle. This is a name that the industry is using at the moment. The main component in your car will not be anymore the mechanics. That will be the software actually driving the mechanics. Mechanics we know how to do. We did it for years. It's not evolving that much. But the software actually controlling the mechanic is. And this is a new trend. So we will have multiple OS, RTOSs, and etc. in a system. And we will have big cores, so Cortex-A cores, real-time cores, and also some small microcontrollers. Okay. Whoa. Sorry for that. Small microcontrollers. So the car itself will become heterogeneous. And all those systems will be connected, and for most of them updatable. So to show you the potential complexity of what the car industry is seeing in the future, you have on the right what is the SOFI project architecture at the moment. What you see there is an architecture which is hypervisor-based, but an architecture which is also connected to the cloud. So the system is not only complex in the car, the system is complex overall because it's connected, and part of the development will be done in the cloud for easier development and for easier pushing to the cars. What we need to achieve that, and that's what the industry thinks, is to standardize the software stack. Main goal of this is for the industry to focus on what they know and what they want to sell, that the added value on the car. And the base software stack that they use on those big cores is not the added value. That's something common to any car manufacturer. So there are several projects ongoing out there to try to standardize this base software stack. First example is SOFI, where car manufacturers, tier ones, software vendors, and CPU vendors are putting themselves together to try to define a base software stack. This is the example that I showed you in the previous slide. Then we have global platforms, which is focusing on the secure part of the car. System ready, which is focusing on having a standard to try to define how a system should start and how it should present itself to the next software stack. We have FFA that I presented yesterday, which is starting to standardize the interface between the normal world and the secure world so that your software stack in the normal world is independent from what you use in the secure world so that you can switch from one OEM to another OEM or one SIP vendor to another SIP vendor. And there are other initiatives are there. So safety certifiable open source is becoming a possibility. Why is that? It's because of those standardization. Everybody wants to have the same software stack, and as a consequence, they are looking into open source so that they can certify bigger software stack, sharing the cost between all the interested industrial parties. And lots of open source projects already started. We had a presentation yesterday which introduced you about Zephyr going to safety, ELISA project, trying to help people using Linux in safety project, and the Xen project where me and Stefano are leading the FuSa group, which is working on safety aspect for Xen. So Xen at ARM. Xen is a key component for automotive and critical application at ARM. Xen is the reference type 1 hypervisor for ARM. It is also the hypervisor chosen by Sophie as a reference hypervisor. And Xen is used internally at ARM to do automotive demos, proof of concept, and internal design. So we have several projects ongoing at ARM on Xen at the moment. Some of them are visible on the mailing list because we started to push some patches. Some of them are long projects like PCI pass-through. And ARM has a team of people working on Xen.
At AMD, Xen is the open source reference hypervisor for embedded and automotive for both ARM and AMD x86. We have an in-house team to develop, engineer and enhance Xen for embedded and automotive use cases, and you might recognize some of my team members from emails on the mailing list. Xen is also supported to our customer via forum premium technical support and engineering. So one thing that is interesting that I'm going to highlight because it's going to have an implication for safety is that we do have customers on the classic Xilinx side that are using today Xen with hard real-time workloads to do separation of hard real-time VMs, FreeRTOS typically, from Linux. So, not all open source projects are equal, right? And Xen has a very strong history of caring about security and isolation. And that is why, it's easier, not easy, but easier than other projects to safety certify or making Xen safety certifiable compared to any other project, open source project on GitHub that might not even have a defined security process, as an example. So let me start by going through some of the key components of our processes that are actually directly impactful, positively impactful to safety and safety certifiability. So first of all, we have an extremely strong review, code review process. We are famous for being sometimes too strict, and we get regular complaints that our reviews are too strict. Now, these might not be maybe overall that good, but from a safety perspective, is exactly what you want. You want to be very strict, and in no circumstances let patches in, even if you are close to a deadline, whether that is a company deadline, and bonus are impacted, or whether it's a Xen project release deadline. We never, in recent memory, have let bad patches get committed. We also have what the safety guy call an independent panel of experts doing reviews, where independent is the key word. You see, what happens in a company is, you do have reviewers, usually in a proprietary environment, but what happens is you are, a couple of weeks from the code freeze, and everyone bonuses are at stake, and things get committed somehow, right? Even if they're not maybe top quality. And that's something, like I said, doesn't happen in Xen project. Everyone works for a different company. We have different deadlines, and simply this kind of dynamic, cannot work. We also have a very strong security process. Now, it's very detailed. It's famous industry-wide and has been used as a model for many other security processes in open source projects. This is exactly the kind of thing that helps. Actually, documenting the security process is one of the requirements of ISO 26262. I think it's true that security and isolation are top priority for Xen project, and a testament to that is we have companies and projects like CubeOS that are based on Xen, and they're security focused. So Xen is the engine behind many security focused products and projects used today widely. We also have full traceability of commits. So when your colleagues come to your desk and tell you, please commit this, you commit it, and then nobody can explain why it was done because he left the company. That also cannot happen, because everything that gets done, everything that gets reviewed and committed is done on the mailing list, and we have archives that go back 20 years. That also helps with safety certifications. We have CI loops, two now. One is OSS test, testing Xen on real hardware, and we also have GitLab that does more than 100 tests today. And Xen is widely used in production. That also helps, and is used in production. I mean, not to run just not to run non-critical workloads, but also to run critical workloads. Maybe not safety certified workloads, but still critical. And an example was the Xilinx customer I was telling you before about real time. But we also have, again, cubes on the desktop. That it performs an essential function of separating an environment to handle sensitive information from the environment when you casually browse the web. That's still a critical function. Or Amazon AWS or the cloud or data center where you have multi-tenancy is still a critical function. So overall, these are all the reasons why making Xen safe is viable. And AMD is working today on making Xen safety certifiable for AMD platforms, both ARM and AMD x86. We are targeting IEC 61508 SIL 3. So you might remember Kate's slide from yesterday. IEC 61508 is a standard for industrial, and SIL 3 is the highest for industrial. And is actually there is SIL 4 even there, almost the highest for industrial. And this is equivalent of ISO 26262 ASIL D, which is the highest for automotive. So. And they're very similar between each other. But the key here is, and I cannot stress this enough, the certification, the certifiability work that we are doing is based on the upstream Xen code base, upstream Xen releases, and upstream Xen processes. So what I mean by that is now we are not taking Xen, fork it, making significant changes internally, have an internal team working on Xen, and then document all of our internal processes as well as our internal releases. That's not what we're doing, and that's what actually Kate, if you remember from her presentation yesterday, she was exactly talking about open source being safety certified today, doing exactly this. So people kind of inherit an open source code base, make it their own, and then bring it to safety certification. And this is not what we're doing. So we are, when we are going to explain what is our review process, we are going to explain what the upstream Xen review process is. And when we explain who our reviewers are, we are going to mention people that don't work for AMD, like Andrew Cooper. So it's going to be an upstream Xen project-based safety certifiability work. Now, this is great for the community because that means we can give back a lot more. Right? We can make a lot of our efforts upstream directly. It's also great for us because if we forked it, we will never be able to update it. It would be a one-off effort. It will be frozen in time and never updatable. And that's not what we want. So what we want is to be able to update it in the future, maybe not for every release. It's not going to be zero cost, but still be able to update it with a reasonable effort. Most of the things, a lot of the things will be open source, not just open source, but upstream. We're going to try to make them upstream. Also, not everything will be. Some of the safety certifiability documents and artifacts will be for AMD customers. Things like MISRA C, however, that's going to be fully upstream, and we are already, the work has already started and is ongoing to make Xen MISRA C compliant. We are also going to improve public interfaces documentations. Public interfaces includes a lot more interfaces than you might think. It's not just hypercalls, it's also the boot interface, Xen command line, also interface to the hardware. What are the hardware interface we support and which one we don't? As well as GitLab CI testing. So we're going to use GitLab CI for our test, and some of our tests will be upstream and will be benefiting Xen project testing directly. So you might be curious about what is the scope for this project, and I'm going to try to give you some of the interesting details. So we already discussed about the certification target, ISO 26262, ASIL D, and so on. ARM and AMD x86. We're going to target the newest components only. Things such as we're going to take for granted hardware that is virtualization extension capable, of course, with the AMD V, VI, and on the x86 side, on the ARM side, SMMU v3, Geek v3, newest components. We do not think it's going to be a lot of work to move it to future generation of hardware, and that's because, in Xen, we don't have that many drivers. Yes, once in a while we need to move from Geek v3 to Geek v4, or from SMMU v3 to SMMU v4, but it's not that common, not that frequent, and not that many drivers. So we believe it's going to be able to be portable to future generation with limited efforts. We are also going to include the basic components for memory sharing and VM-to-VM communication, namely the event channel and ground table. There is no OS hypervisor dependency, so you will be able to run anything as a guest, whether that is Zephyr or whether that is Linux. So let me explain a concept that that's interesting. So, and this also was in Kate's slide yesterday, if you caught one of the table. So QM from the safety certification expert means that it's not safety certified. If it's not safety certified, like let's say a normal Linux distro, Ubuntu, or Android, they will be QM, classified as QM. Something that instead some level of safety certification could be, for instance, Zephyr in the near future, or one of the proprietary RTOSes today, that will be for instance, will be called the safe OS or the safe environment. They are not always at the same level of ASIL. So ASIL, well, it's how safe it is. So, as an example, in automotive, Xen is targeting ASIL D as in Delta, but you could have a safe OS that is ASIL B as in Bravo. That is relatively common, and B as in Bravo is a lot easier to achieve than D as in Delta. So going back to these slides showing Linux and the safe OS, this is a common use case. It's a common use case because you're using the hypervisor to separate a safe environment from a QM environment, like Linux and Zephyr or another RTOS, right, as a safe OS. And one thing that makes Xen interesting, and all of you that you are here at Xen Summit, I think you know that Xen can do this, but typically not all of them, or maybe not many, of the proprietary hypervisor today that are out there that are certified can do, is we can run multiple safe OSs, we can run multiple QM OSs, and we can mix and match in any way. Because we can have any number of Zephyr VMs, any number of Linux VMs, do direct assignment to any of these VMs and let them access devices. And that makes it very, very flexible. We are going to use Hyperlaunch or DOM zeroless, the same feature on ARM and also AMD x86 for the domain creation. So the idea is all of the VMs will be created at boot time with hyperlaunch type of boot. No VM creation at runtime, no new VM creation at runtime required. Now, that also means it makes things easier from a DOM zero perspective, because at this point, you don't necessarily need DOM zero anymore, or at least it doesn't have to be Linux, or at least it doesn't have to be safe, or doesn't need all the Excel tool stack, or only a subset, right? You might want, it's more like a control domain or a configuration domain, right, in this environment, because if you don't do any more domain creation, it's not the all-powerful, DOM zero we are all used to. Moreover, we need to protect, we very likely need to protect somehow, either with XSM or other means, the safe VMs from DOM zero, right? In many configurations, we don't want to let DOM zero affect the safe OS for obvious reasons. Even if DOM zero was safe, you wouldn't want one safe OS to affect another safe OS. There is a concept that is very familiar to, I think, people in Zen, because we really always cared about isolation. The safety people call it FFA. That stands for freedom from interference. And the role of the hypervisor here is to make sure there is freedom from interference between VMs, including from a safe VM and another safe VM. On the x86 side, we are only going to do PVH. Now that's, this is very easy to explain why. So PV guest interfaces require too many hypercalls. Every interface, and we'll see, need to be tested in safety. So the more hypercalls you have, the more tests you need to have. So safety certifying PV will be a much bigger effort. HVM is fine, has a very different problem. There is QEMU, and you definitely don't want QEMU, right? The problem of QEMU is there is no easy way to fit it in a safe architecture, because where do you run it? If you run it in DOM zero, you will need, not even DOM zero safe will be enough. And then even QEMU will need to be safety certified somehow. It makes the architecture very complicated. So it's much easier to go with PVH, where QEMU is not needed. Maybe you could pull it in to run virtual backends. That's okay, but it's not required to make a guest boot. It's a fully static configuration. So you know beforehand the number of VMs that you're going to run is always the same. It's going to be 2, it's going to be 4, it's going to be 5, depending on your use case, but it's always going to be 5. It's never going to change. Real time definitely supported. It might not be, automotive, depending on where you run it, is not always important. In industrial, it's almost always important, and we definitely need to support it. Okay, I'm going to try to talk a little bit about how I think people are going to use this. Now, as you know, device assignment, device sharing, device assignment, these kind of things, the building block in Zen are actually very small, and we're going to have them. Like we are going to include device assignment, we are going to include device sharing with PV drivers or Virtual. That's because it's very easy from an XM perspective. The building blocks in the hypervisor themselves is they're very few. So that are included in the scope of this project. The complexity is of course inside the guests, where you need to run the front end and the back end. So I do think devices should be, most of them, directly assigned, because that is obviously assuming that the hardware is safety capable, there is an IOMMU that does its job, is the easiest configuration to make safe. We are also going to have VM-to-VM communication. This is also a good one because it's small and easy. It's about byte exchange. It's not about exposing a full virtual device to other guests. So it's also easier to prove that it's safe. Exchanging bytes is not crashing one end or the other. And finally, device sharing. Device sharing is a difficult one because it's complicated. So one of the keys that we want to enable is unprivileged device sharing. What I mean by that is the device sharing where the backend does not have to have full privileges over the other guest. And to do that, obviously, one way is PV drivers, but also Virtio with grants is definitely one of our key targets. So I talk a little bit about device sharing, and VM-to-VM communication. So VM-to-VM communication, a few key properties that makes it desirable is very simple. It can be defined statically. There is no OS dependency. I mean, every OS can use a shared memory region, right? And you can configure it in a way. It's up to the user to configure it, but it can be configured in a way to be safe, such as to make sure indexes from one end cannot be written by the other end and things like that. So it's known to, there are very well-known mechanisms to make plain shared memory safe. Device sharing is, like I mentioned, is more complicated. So, and the impact on the overall safety is interesting. It needs to be carefully thought through. So let's say that you have something simple, something like a GPIO or CAN bus. So these kind of devices are very simple. The driver is also small and simple. So the Virtio or PV backend for it would also be small and simple. For something like this, it would be conceivable to put assign the device to Zephyr, have the driver in Zephyr, and run the backend in Zephyr, and safety certify. Why? Because the overall code base will be limited. You might care about your GPIO for safety. Some critical information could come via GPIO that triggers some alarm bells in your car that are considered safety critical. So you put that part, which is safety critical, in the safe OS. It kind of makes sense. And then if you really need to expose GPIO to the other VMs, you can do it with Virtio or PV, making sure, obviously, that interface is not a vehicle for attacks. But another example, which is exactly the opposite, is the GPU. And then, if you take the AMD GPU as an example, that as a driver that is millions of lines of code, right? You cannot put millions of lines of code of a GPU driver in Zephyr, which is less than, 20K, overall. So it is not, and safety certifying it would be a massive effort. So, and also, I mean, one of the things, this is about the actual safety of the system, not of the safety of the system on paper. So imagine you have a proprietary OS as your safe environment, and you want to port your GPU driver to that safe OS, right? The driver in Linux has been running for millions of hours in production, in cloud, client, desktop, all based on Linux. Now you're porting this driver from Linux to, I don't know. I can tell you that the end result is going to be less safe than the original because the porting effort will only introduce bugs. It's not going to fix any bugs. So now you have the same driver as before with more bugs in your safe environment. It's not a good idea necessarily. Instead, with Zen, you can directly assign the GPU to a Linux VM, run your Linux driver in your Linux VM, where it's its native environment, is where it has been developed, is where it has been tested, is where it has been run, and is known to work well. And then you run the backend in your Linux VM, and you have the other VMs connect to it. Now, that works very well, and it's definitely something, that's maybe something unique to Zen, because many of the other, not all other proprietary hypervisor can do this. However, one thing that you have to be very, very careful of, things are never too easy. What if the graphics is partially safety critical? An example is if you're using the GPU to render the dashboard. The dashboard is the display in front of the driver, the one with the accelerometer, speedometer, and other metrics. So if that is now going through Linux and Linux is QM, as from a safety perspective, that could go away at any time. So the driver could have no dashboard for a little while. So obviously, you know, as a user putting the system together, you have to carefully really think through all the angles. And here, for instance, you could try to mitigate it by rebooting the Linux backend very quickly and prove that it can come back online in 1 or 2 seconds. Or you can try to have an emergency display somewhere, you know, a Judy display that comes up very quickly. But yeah, so, and this is why, you know, as Bertrand here also knows, is you know, when you think about safety, there are very many angles to think. So it's not just one single aspect, and it's sometimes difficult to pull the whole system together. So this is an example of what could be potentially Xen-based system which in a safe environment where you have Xen creating all of the VM with hyperlaunch, ARM or AMD x86. We could have a minimal DOM0, you know, QM, non-safe, so you will have to make sure using XSM or something else that it cannot affect your Zephyr environment, which is the safe OS, the green VM. Then we have sort of a driver domain VM, the yellow one, with Linux, again QM, with the largest drivers, such as GPU and audio. Not necessarily, this is not required. So you could have all the drivers in Linux, but they say that, you know, you're worried about your graphics stack. No worries, move it out. Run it in DOM-D. And then both Zephyr and Android connect to the PV backends or Virtual backends running in your you know, DOM-D domain to get access to the graphics and audio. And you directly assign things that are more critical, like the CAN bus or GPIO, directly to Zephyr using pass-through. Okay, so I have some details here on the slide, which it may be too many details, so I'm going to go quickly over them. But here is our safety certifiability plan for Xen. Is divided in 2 phases. The phase 1 is where what we're doing today is called safety concept. And this is where, well, I'm going to give you more details in a second, but this is where you provide your plans and some example of the artifacts to the assessors. Now, the second phase is a big one, where you need to pull together all the evidence. And here are some examples of the artifacts and, in general, things that need to be produced as part of this effort for phase 1 and also phase 2 in the next slide. And you can see there are a lot of plan documents in phase 1. And at the end of phase 1, the goal is to receive a safety concept approval letter from the assessors. And basically what it tells you is you are on the right track. If you deliver on these plans that you made, on this concept that you made, you're going to get to the end, right? And the phase 2 is the one that actually produces all the tests that are required and all the other artifacts that are required. And, you know, if you are an engineer that hasn't worked on safety before, and you probably see this slide, I bet it doesn't mean much to you. And the reason is all of these documents that you see here, like software verification specification, just to name one at random, has a very specific meaning in ISO 262. So if you study ISO 26262 and you see software verification specification, you are like, of course, it makes sense that it's in phase 2. But if you are a normal engineer like me, I read this and it doesn't tell me anything. And this is why we pull this other slide together. Well, we're trying to explain in plain English what are, or just to give you try to give you an idea of what these artifacts are that needs to be produced. So one first set of documents that needs to be produced is the requirements. Now, requirements is what the set of requirements are is really a description of all of the expected behavior of Xen. So how can you test and make sure that Xen does what we say it does if we don't know what it's supposed to do? So first, most important thing is document in detail everything that Xen is supposed to do. Everything that Xen is supposed to do in normal configurations, depending on boot parameters, in response to interface hypercalls, for instance, or other interface probing, but also behavior when something goes wrong. What if there is an error? What Xen should do then, right? What is the recovery plan if there is an error? So this is what the requirement is. The list of requirements is a list of all of the expected behaviors. So software architecture specification is a description of Xen in his architecture and the various components and internal interfaces. MISRA C. So MISRA C play a key role because one of the important things that you need to prove is that your code is safe. And one of the ways to prove it is that you are following strict safe coding guidelines. MISRA C is exactly that, the safe coding guidelines. Verification and validations together are really all the tests. So in safety, you need to prove that you test everything you're going to run. And I mean, if you think about it, it's kind of normal, right? So if you want to make sure that your software behaves as you say it behaves, prove it, right? Test it, show it. Show that you are testing everything you say that is an expected behavior, and that the outcome of the test is what you say, what you said before that it should be, right? So that's what all the tests are meant for, and this is by far the biggest activity overall, because you need to, the tests that we're going to have to probably write for Xen they're going to be in the thousands to cover all of the configuration and all of the interfaces, all of the drivers. There are other things that are more about documentation of processes and tools, like the software tools classifications and qualification report. This is an interesting one. Is one of the less obvious. So this is about listing and documenting all the tools that we use, either for writing or testing or code, and you think, why? And the reason is because there is a risk these tools themselves will be introducing bugs. So as an example, if you use a buggy compiler, you might have your code that is super safe, but your compiler is introducing bugs at compilation time. And what if your code only compiled with one compiler, which is buggy? Now your code is not safe. And that's why this tools classification document is also important. Say, famous or infamous, because it's very difficult, FMEE document is a failure mode analysis, and this is where you go in details on what happens if there's a failure, what happens if can you actually recover, or is the behavior correct in case of failures. And finally, there are all the process control and safety management documents. So these are documents to document our review process, document to in terms of are we using revision control. I think nowadays you are not going to find an open source project that that doesn't use revision control. But people were doing safety before Git, right? So this is to make sure things are at least revision control and testing plan is all correct. And also there is knowledge about safety, right? So one of the things that we have done with the community already is to do a MISRA C course for some of the key members of the community, because it's all good to say that you're doing MISRA C, but if you do MISRA C and nobody that does reviews knows MISRA C, is not that useful, right? So there needs to be also a plan to handle knowledge and knowledge transfer in the community. Okay, so overall, the rough estimate is that for a generic project of around 50,000 lines of code, 65% of the effort is about testing and tests, and 35% of the effort is about documentation. It roughly, takes about 2 years, 2 years and a half to complete. And like I mentioned earlier, so the plan for this has always been to be able to update the artifacts. So because it's all based on upstream code bases and processes, we should be able to take all of these artifacts, all of the tests, and move it to a newer release of Zen. And yes, maybe we need to update a couple of tests. We might need to add a couple of tests. But overall, it will not be a major rework of everything. What is the impact on the community? So I do think that the impact on the community is very positive, in my opinion, for a couple of reasons. So first of all, this enables Zen to enter new markets and segments that was impossible before, from industrial safety, even medical devices, or of course the transportation industry in all its forms, from automotive, railways, as well as even avionics maybe one day. And obviously the more users we have, the healthier is the community. So that's obviously one advantage. But also, if your community, and I do think, I am sure that the Zen community care about quality of the code, care about not having bugs, care about, robustness above everything, then this work is definitely pushing the community in the right direction. With MISRA C upstream, we are already starting to see positive benefits on the maintenance of the code base and quality of the code base. We are going to introduce MISRA C checkers automatically as part of our testing, and that's going to also make review easier. It's going to catch automatically all sorts of trivial coding mistakes that today the reviewer needs to spot manually still, one by one. We're going to have far better documentation in the Zen 3 of all of the interfaces, and we all know that documentation of at least public interfaces like hypercores and boot interfaces is super critical. And whenever one of those interfaces is not documented, you always find someone that used it in the wrong way, and now you don't know which one was the right behavior anymore, because it was not written anywhere. So better documentation of the interfaces definitely is going to make our open source community better. And finally, testing. Testing is a funny cliche that in open source, is never done right. And if you remember the good old days of the early days of Zen and early days of Linux, it's true. Like, we weren't doing really any testing upstream, right? Nowadays, I think open source as a whole grew significantly. Many of the open source projects are doing tests, including Zen, including Linux, including QEMU. But definitely this is not at the level that we actually need for safety. We need way more tests. And we are going to add way more tests here. And we're going to make sure it's far harder to break Zen at any given time, or ensure any Zen release is in better quality. And I think with that is the end of my presentation. So, do you have any questions for me or Bertrand?
On one of the slides, you shown connecting backend running in Linux to a save VM.
So you have a good point there. I think let me add a couple of things here. I realize now I forgot to mention. So one of the things that are very critical to make this work is that the backend cannot have all privilege over the front end. Otherwise, it could crash it at any time. So this needs to be using, if, for instance, in the case of Virtio with grants or with a pre-shared memory region to make sure the privilege, the backend is not privileged, right? Also, the front end in Zephyr needs to be written in a way so that if the backend crashes, the front end, is not affected. Obviously, if the backend crashes, you're going to lose graphics, but the front end cannot crash, right? The front end needs to be able to detect that the backend is not running and, continue without graphics. Yeah. Sorry, I realized. Thank you for giving me the opportunity.
Yes, so that was exactly my point. And historically, backends are usually assumed to have full control on the front end, and front end are not written with assumption then that backend. So this would need to change. I think in the upstream then it is the case for network and disk front ends already, but others probably will need to be improved.
No, you are exactly right. So in And that's a fantastic question. So PV frontend and backends have an advantage over Vert.io because they were written with grant table in mind, which enable the backend not to be fully privileged. However, many of the frontend and backend were not written this way, right? And backend and disk and the network and disk, I think they were written with the backend not to have privilege, but not all. And an example is the 2D frame buffer that we have called XenFP that requires privilege today, I think. Vert.io also was written to have privilege, but we are adding grant table support. And right now, Vikram in my team is working on also running, testing Vert.io backends in DOM-D, like out of DOM-0 on purpose to make sure it can be run without privileges.
Just on this one point from the safety point of view, it's okay for a safety application to use a non-safety feature as long as the safety does not depend on it, which means the safety application design here should have something saying, I use this, if it's not there, it's not impacting me, I can continue my life and provide the safety that I need to provide. So, for example, displays are a good example in safety. You display information, doesn't mean that the role that you have on actors and sensors and etc., you cannot continue to do if the display is crashing from time to time. So in your safety design, you will include something saying, I write something in memory, I signal to the other side that there is something to display on the screen. I somehow do not care really if it's displayed or not. That's an information, that's not a safety feature. In cars, there are some displays which are safety critical, some others which are not. And for example, your speedometer, it is safety critical to have it right. It's not safety critical to have it displayed. If it's crashing and you're rebooting it, that's okay for now. It might change in the future. What is critical is for your emergency signs to come up if there is something going wrong in your engine. Those ones, you have to display them and you have to make sure that if something is going wrong, those are displayed. The speedometer, you need to show it right. If you don't show it, that's okay. You can reboot. But you need to show right information, not the speed you were at 1 hour ago. Yeah? Yeah. Sorry.
I have a question and a remark. The question is regarding the aspects you talked about for compilers and obviously extending to all the tool chain that is involved. You mentioned compiling with a buggy compiler will of course basically void any security considerations of the source that were made. But there is not going to be any bug-free compiler.
I can answer on the compiler side. So, depending on the level of safety that you want to go to, the constraints on the compiler can be different. The minimum that you need to do is qualify your compiler. For qualification is not certification, so you give it some examples of all the combination of functionalities that you use in your compiler and you check the outcome. You do not cover all, you cover one example of each feature. That's qualification of the tools.
And GCC has been qualified several times.
GCC has been qualified up to some extended functionalities on GCC that might need some extra qualification. The best functionality of GCC, the tool chains that are included in the GCC open source group are enough for qualification, at least on some level of safety. Then, most of the safety standards also depend on the fact that what you are testing is not your C code. That's a binary that was generated out of your C code. And if this binary is behaving as you were expecting from your C code, some level of certification includes that into the fact that the certified product is not your C code. That's a binary that you generated out of your C code and that you will test from the external as a black box. You will test the final binary. This way, you cover everything. If you go to highest level of certification, then for some part of your code, they mandate to have a certified compiler. ARM has one, for example.
Okay, yeah, thanks. I'm surprised that GCC has qualified because having worked on GCC a little in the history surprises me because the quality isn't all that good.
But qualified is not certified,
Yeah.
right? And I think CCC, I mean, I don't want to speak out of terms here. GCC has also been certified, but that is a lot of work and only in very specific cases. Like I think GCC for, yeah, anyway.
GCC 2.9 was safety certified for avionics and has been used for 12 years in avionics.
Did you say 2.9?
Yes, I said 2.9. From 2000 to 2008, we used GCC 2.9. I think 97 at some point or something like that, because it was safety certified at some point. There was so few functionalities that it was okay. GCC 3. Something was used in avionics certification for years, using old versions because every company had inside a set of tests to qualify GCC, and it was accepted that it was an old version of GCC used in many projects, and we had some qualification tools which were analyzing the end binary, and we did not use some of the GCC functionality. For example, in avionics, if you go to dial C is the equivalent of SEAL 3. Dial C is a system that is critical, but if it's crashing, it's bad, but you will not crash the plane.
So the plane have, just to be one thing, so at Kate presentation covered yesterday, but the plane compared to industrial and automotive have one more level. There's basically one more level of difficulty compared to what we're targeting here, for example.
What we do on that is we compile, at dial C you compile with O2 is accepted, dial B you compile with O1, and dial A you compile with O0. Because you cannot achieve full coverage of your code with GCC optimization, because there is no link anymore between your C code and the assembler code. So you have to disable optimization in GCC, which has a lot of impact.
Indeed, I don't think we build at -0 at all right now.
I know we don't, but we don't target dial A in the future.
Okay.
Dial A is you cannot crash because it will kill life. That's the highest level of certification. In comparison to what will be done here, dial A certification cost, the estimate in the industry, is around 16 hours, not for development, for certification per line of code. So that's a level which is achieved only by proprietary RTOS, which are reduced to the bare minimum when it's needed.
Okay, yeah, thanks for the additional insight. The remark. Earlier on in your slide, Stefano, you had a remark about all communication in public. Some of the more difficult decisions we take in private when we're working on security issues. Something to potentially consider is that we make such communication public after the fact.
I don't know if it's as necessary. So I think what I think from this effort point of view, what is important to prove is we haven't committed a patch without reviewing it, or another thing that maybe we do that is slightly against the rules is changes on commit. I mean, if we make major changes on commit, that would not be good because then nobody reviewed them, right? So I don't think we necessarily, especially because we have a good reason here for security vulnerability handling, we necessarily need to have the full history of the go back and forth on how that commit was achieved, as long as we trace the tags, the act by, the review by. But you're right. I mean, that's a good point, and I'll investigate if that's necessary, that we could consider making it public after the fact.
I think for the security process there are two parts. First, it's tracked on the patch who reviewed it. So it's not different from the official process. The comments are not public before, and then the XSA documentation is giving the reasons and aspects. So a combination of that should be acceptable. I know that it's done this way in other closed source projects where the security process is different from the safety one. But it's acceptable because it's tracked, there is a process, there is an end decision, and in the versioning system, you can check and you know that it's related to XSA, so you can go to the XSA documentation. I don't think we have an issue there. In fact, we are quite good there.
Even better if that's okay, yeah. Thanks.
Public does not necessarily mean for the safety that it's public everywhere and you see it on the news at CNN.
Great, thank you. That was up. So.